All right, video number 2. So what does 95% confidence really mean? So what we said was that we were 95% confident that when our sample was 51 point whatever, that if we stretched out 2 standard deviations, we're 95% confident that we captured the true proportion of infected CVANs, even though we don't really know what the true proportion is. So another way to look at it is, like we said in the first video, if all of us went out and collected values of CVANs, all of us would get a slightly different sample proportion. So all of us would have a slightly different interval, and we would all feel like we were 95% confident we captured the mean. So this little graphic down here is kind of a good representation of that. Pretend like each one of these is a different one of us going out and collecting a sample of CVANs. So the red dots are each one of our sample proportions. I got 51.9. You might have gotten 52.3. You might have gotten 50.8. So all of us got a different one, but we all did a 95% confidence interval. So see how all of us expand out the same width right here for our confidence interval. So this green line right here, this is the true proportion of infected CVANs. We don't know what that is, and we will never know what that is, but notice how it remains constant all the way across. Let's pretend that the true proportion of CVANs is, 53.2. Okay, so when I got 51.9, maybe this is me right here. Actually, I was a little below. My sample was a little below. But when I cast out my net for my 95% confidence, I still captured the true proportion. Okay, but then over here, look at this one. Maybe this person, their sample was actually like 56.3. So whenever they cast out their net, or whatever it is, these are just numbers I'm making up, they didn't actually capture the real proportion, which again, remember, we don't know what that is, but they didn't get it. So only 95% of the time are we going to get it. There's still going to be some dud samples. Yours was really extremely low. Do you know it's extremely low? No, not unless you take 12 samples, which you don't have the time or money to do. So not all of our samples are going to capture the true proportion, only about 95% of them. Okay, so I think this graphic is a good one, and you never really know where you sit. That's why we're only 95% confident that it's between here and here. Okay, so this section's called certainty versus precision. So there's always this delicate dance when you're making a confidence interval that, okay, well, if I wanted to cast my net as wide as possible, I'd just say that the true proportion of CVANs is between 0 and 100. I'm 100% confident. So look at me, I'm 100% confident. But my range is so wide that it doesn't really give me any information. I could say that I'm 12% confident that it's between 50 and 51. Well, that's great. I have a really small margin of error. I've narrowed my window down really tiny, but look, I can only be 12% confident. So the dance of a confidence interval is always between how confident do you want to be, but how wide do you want your margin of error to be, okay? Remember your margin of error. In this case, we used 2 standard deviations because we wanted to be 95% confident. If I wanted to be 99.7% confident, I would use 3 standard errors away. But my margin would be a lot wider because the more confident I want to be, I have to cast a wider net to make sure I'm more confident. If I'm okay being less confident, then I can have a smaller margin of error, a smaller interval, and be less confident about that. Okay, so confidence and margin of error are directly related. As one goes up, the other goes up. As I'm more confident, I have a larger margin of error because I want to have more wiggle room to be wrong. As my confidence goes down, my margin of error, my interval width, goes down. They are directly related. So a lot of the questions on the AP test, the multiple choice section, some of them will be calculating confidence intervals. Well, some of them will be these relationships. What happens if I increase my sample size? What happens to my confidence level? What happens to this? What happens to my margin of error if I want to be more confident? So we need to understand how these work so that we can answer questions like that and not just push buttons. Okay, so look, this little guy down here, now he's going to be within 3 standard errors, so that's 99.7% confident. So he's more confident, but in order to be more confident, he had to use more standard errors, meaning larger margin of error, meaning wider confidence interval. The more confident you want to be, you have to catch a wider net to make sure you capture that true proportion in there. Okay, so this delicate balance between certainty and precision will always be something you have to work with if you're doing these in real life. When we're doing them in the stats classroom, they'll tell you, create a 90% confidence interval, or make your margin of error be 4 percentage points. So they'll tell you what you want and you just have to go for it. Okay, the most common margin or confidence levels are 90, 95, or 99, but you can also have 98. You can have any of those in there. Okay. Okay, so when we were doing our 95% confidence interval, we said that 95% confidence means that I'm going to be within 2 standard deviations because we were using that 68, 95, 99.7 rule. So that's fine. That's just an estimate. It's not perfect. So we're going to learn how to find our critical value, which is our z-score, based on our normal model or on our tables, whichever one you want to use, so that we have accurate numbers instead. So here, this is a really important process here. And once you do these a lot, you'll know what your critical values are. You'll have them memorized. But in case you have, just a slip or something, we need to know how to calculate them. So we have a normal model. And remember, I'm starting in the middle. My p-hat is going to be in the middle. And I want to be 90. I'm going to do a 90% confidence interval. So that 90% is in the middle. So this is 90%. Okay, well, what's left out? Well, 10% is left out if I want to be 90% confident. So I have to divide it by 2 because I have 2 ends of the graph. So 5% is left out on the bottom half, and 5% is left out on the top half. Okay, so now that I know, remember your normal model, your tables, your green charts, they only do below. So you can find your z-score down here for the below. I'm giving you a percentage, so you want to use inverse normal of 5%. And you can either go type that in your calculator, second distribution, inverse normal 0.05, and it will bring you back negative 449 actually. So that's where we got negative 1.645. Inverse normal of 5% because 5% is left out. Now remember, your margin of error is always plus or minus because you have room on the bottom and room on the top. But the normal model is symmetric, so you just have to find one and then change the sign to find the other. So plus or minus 1.645 would be my z-score that I would want to use from a normal model. If you want to use your charts to look it up, you can do that too. It's the same exact thing. You just go into the body of the chart and you look for 0.05 in the body of the chart, and then you look out and up, and it will say negative 1.6, and it will say like this will be 0.0, what will it be, 0.00, and this will be 0.05. So you'll know it'll be between 1.60 and 1.65, so that's where I got the 1.645. So either way you want to do it, using your calculator, second distribution, inverse normal, or using your z-tables by looking up 5% in a table and looking out to find the appropriate z-score. And then I can do this for anything, okay? I could also do this if I wanted to do 95%, I would just look up 0.25 on the outside. If I wanted to be 70% confident, which doesn't happen very often, I would look up inverse normal 15% because there's 15% on the low side, 15% on the high side. Okay, so I'm doing this to find my z-score, which is how many standard deviations away do I want to be. So we call it our critical value because it's telling me how wide am I going to cast my net. Okay, assumptions and conditions, you know from chapter 18 that we already have these, that we have to check these assumptions and conditions for every time we run one of these tests. Luckily, these assumptions and conditions are the same as they were for chapter 18. So really two assumptions. I want to be independent and I want to make sure that my sample size is large enough. So to check our independence, we're doing the three things, that we've already done before. Okay, so is it plausible to think that these are already independent? Is one CFAN is independent of another? Well, in this case about the CFANs, it might not be. If the disease, I don't know how CFAN diseases work, but if they're contagious, then it might not be. If one is infected, it might affect the other one. So that's a little bit tricky to work with right there. You might have to say that. CFAN illnesses or whatever you're talking about, infections, might be contagious. CFANs might not be independent of one another. But remember what we talked about in chapter 18. If they're not independent, that's where the 10% condition can kind of save your tail. Okay, I'm sampling 104 CFANs on the Los Redis reef. Therefore, 104 is less than 10% of all the CFANs. Okay, and then the randomization condition will always be there, because if we don't take random samples, then we don't have good data, then we're not doing this in the first place. Okay, you will either have to assume randomness, or it will say in the problem. Both questions on your chapter 18 test said it in the problem. Random samples of 100 and whatever frogs or whatever it was. And a lot of you said, I'll assume random. You're not assuming crap. It said in the problem that they were random samples. So just quote it from the problem. Okay, so do I think these are independent? Even if you said maybe not, you can still get away with it with the 10% condition. And then they're always going to be, you always have to make sure your samples are drawn randomly, otherwise your data is bad. Okay, the other condition is one you are also very well familiar with, your success failure condition. So you're still doing that NP times NQ NP is greater than 10 and NQ is greater than 10. So same thing you've been doing for a while now. Okay, once all these conditions are met, again, we're naming what we're doing here. So we're doing the 1 proportion Z interval. We have one sample. It's categorical data. We're using Z-scores for our critical values because we're using the normal model. And we're doing a confidence interval. So here's your formula right here that you've already kind of seen and been working with. We're going to take our sample proportion, P hat, plus or minus, because we stretch out in both directions. Our Z-score, our critical value that we found, and that's found based on how confident do you want to be. And then the standard error. And remember, we're calculating the standard error as square root of PQ over N. Okay, so let's try one. In May 2002, the Gallup poll asked 537 randomly sampled adults the question, generally speaking, do you believe the death penalty is applied fairly or unfairly in this country today? Of those, 53% answered fairly and 7% said they didn't know. Okay, we'll build a confidence interval for the proportion of all U.S. adults who said it is applied fairly. So our P hat, because this was a sample, is 0.53, because 53% said that it was applied fairly. Okay, so our Q hat is going to be 0.47%. Remember, categories you can only have yes or no, success or failure. So since I'm asking the question about who said it was fair, then I will lump the unfair and the don't knows together, because it's either they said it was fair or they didn't say it was fair. Okay, and I had a sample size of 537. So those are the key features that I need here. All right, so first thing, you're always going to check your samples and or your conditions, and you always have to write a statement. A lot of you on your test were just like, check, check, check. No, check, check, check. You got to actually have to write something down. Okay, so first thing is independent. Okay, so this is a Gallup poll. So I'm going to assume that one response is not affected by another. Okay, Gallup is a very good sampling organization, so they're probably going to do a very good job of randomly selecting. So they're probably going to be independent because they're not going to be calling all from the same town or anything like that. Okay, and then independent and random are always kind of linked together. So this quoted in the thing, 537 randomly sampled adults. So I know I don't have to assume random. It's quoted in the problem that they were randomly sampled adults. Okay, 10%. 537 is less than 10% of all adults. So I'm not sampling too large of my population to start messing with the proportions. There's a big enough group there that I can sample 537. And then success failure. So N is 537 times P is 0.53, and that would get me about 285. And Q would get me about 252. So I'm well over my 10 there. So the sample is large enough. So all of the conditions have been met, and now I can run a 1 proportion Z interval. So I'm going to check my conditions. I'm going to name what I'm going to do, and then I'm going to actually do it. Okay, so first let's calculate our standard error. So square root of PQ, whoopsies, that's 47. You can't read that because I have really sloppy handwriting on this app. Over N, 537. So a standard error in this case is 0.022. Okay, so I'm going to be 95% confident. So that gives me a Z-score of 1.96. So if you don't have that Z-score memorized yet, remember 95% confident would mean 5% is left out. So that's 2.5% in each tail. So I could do inverse normal 0.025, and it would come out with 1.959. So that's why I use 1.96. And I use plus or minus. So now I'm going to put it in my formula. So your formula is P hat plus or minus your Z-score times your margin of error. So my P hat was 53% plus or minus 1.96 times your standard error was 0.022. Okay, and then it's just a matter of typing this in. Type it in once with the plus and once with the, once with the plus and once with the minus to get your margin. So 0.53 plus 1.96 times 0.022, and I get, I did plus, so I got my upper bound was 57.3%. Then I'm going to do it with a minus for my lower bound. So 0.53 minus 1.96 times 0.022. And my lower bound is 48.7%. So then I have to write my sentence. And I can write down here. So then what do I say? I say I am 95% confident. Okay, so we're not saying we're 100% right. We're saying 95% confident that between, and then we're going to give our range, 48.7% and 57.3%. And now we're going to put it in context. Of all U.S. adults think the death penalty is applied fairly. Okay, remember that sentence is one you have to memorize. So you put your confidence level, I'm 95% confident, then your range, that between here, and then it has to be in context. Okay, so let's just kind of, I zoomed out, but let's just kind of recap what we did here. We checked our conditions: independent, random, 10% success failure. Once our conditions are checked, you have to name what you're doing. I'm doing a 1 proportion Z interval, and then we can do the mechanics. So remember the formula, the formula we're looking for is P hat plus or minus Z score times your margin of error. So the P hat comes from the problem, Z score comes from inverse normal, and your margin of error comes from square root of P hat times Q hat over N. Type it in for the minus for the lower bound, type it in with the plus for the upper bound, and then write your sentence to draw your conclusion. Okay, so this just checking is what I was talking about how a lot of the multiple choice questions are not about, hey, find this confidence interval. They're about the mechanics. What would happen if you did this? What if you did this? So are these just checking. All right, think some more about a 95% confidence interval that we just created. If we wanted to be 98% confident, what would our confidence interval need to be, wider or narrower? So we had this conversation. The more confident you want to be more confident, you have to cast a wider net to make sure that you caught P, because you need to be super certain that you caught it. So you need a wider interval to make sure that you caught P. Okay, so a higher confidence level means a larger Z-score, means a larger interval. Okay, if our margin of error was plus or minus 4%, if we wanted to make it plus or minus 3%, what would happen to our confidence interval? Well, remember your margin of error, you add your margin of error to get the upper bound, and you subtract your margin of error to get the lower bound. So if I want to make my margin of error smaller, I'm going to make my interval more narrow. So if I'm going to make a narrow interval, I'm less certain that P is within my interval. So I have a lower confidence level because I have a smaller interval. If the Gallup poll had polled more people, what would the interval's margin of error been? Well, remember, margin of error is square root of P hat Q hat over N. So it's basically over the square root of N. So the more people you poll, the more data you have, the more certain you can be. So more people means I am more precise, so I can have a smaller margin of error if I have more people that I'm surveying, because I have more data about them. Okay, you can create your entire confidence interval in your calculator. If that is the question, create a confidence interval, this is the fastest way to do it, is just type it in your calculator. But you do have to know the formula, it's on your formula chart, and you have to know how to use it, because a lot of the times the question is not spit out a confidence interval. It is, here's the formula, what would you change? Here's which formula matches. So you still have to know how to do it by hand, but you can use your calculator if you want to. So we can go second distribution. No, we don't go second. Sorry. You go stat. We've done calculate. We've calculated one variable statistics. We've calculated linear regression. For the whole rest of the year, we're going to go over to test. And we'll spend the rest of the year going through most of these tests and what's the difference between them. But for now, here's the reason it's so important to name them, is so that you know what you're doing. I'm going to go all the way down to A, and because I am doing a 1 proportion Z interval. I have one sample, it is categorical, it is a normal model, and I'm doing a confidence interval. So when you press enter, it leads you through what do you want. X is the number of successes you had. So we're doing back to the CFANs. 54 CFANs out of 104 were diseased, and I want to do a confidence level of 95%. Then I just hit calculate, and it spits out, here's your confidence interval. So I am 95% confident that between 42.3% and 61.5% of all sea fans on the Las Redes Reef are diseased. And it also spits out your p-hat, which you could have calculated on your own. And then you can just as easily change your confidence level, go back and do it again for a 90% confidence level, and you can just kind of quickly calculate that off and on. You still have to know how to do your formula, but your calculator is a great tool to help these things speed up. If that's all you're after is the interval, then by all means, type away. Okay, this is doing the same thing in your calculator, but for the death penalty one that we just did. So remember, we're going to go to stat, over to test, 1 proportion z interval, so that's way down at A. It wants to know the number of people who would have said yes. Well, they gave us a proportion, so I can easily calculate that. They told me 53% of the 537 people in the poll said yes. So I can do 0.53 times 537. But when I do that, I get 284.61. Well, the problem is your calculator knows this is a proportion, so it knows it's yes or no. So you have to go back and type in 285. So they rounded 285 out of the 537 people said that they believe the death penalty is fair. If you don't go back and round, you'll get this error message because your calculator is like, 0.6 people can't say that. So you want it to be 285. And then when you do your 95% confidence level, you get the exact same thing we just got when we did it by hand. Okay? I know a lot of times you guys don't read these what can go wrong sections, but for this chapter, there's a lot of actually information in there. So when you go through, some of these first ones are about those don't say too much. Make sure you write the sentence exactly right. Now, I am 95% confident that blah, 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 all that kind of stuff. But here is teaching you how to go forward and backward. What if they tell you, okay, I need to have a margin of error that's 3%, so I only want my margin of error to go like negative 3% down from the sample mean and positive 3% up from the sample mean, and I want to be 95% confident. How many people do I need to sample? So this is what I was talking about sometimes the calculator's nice, it'll do it for you, it's very quick. But if they're asking you a different style of question, you have to know how to use the formula so that you can solve backwards. Okay, so we're using the same formula from the thing. I want my margin of error to be 3%. 95% confident is a 1.96 critical score. And then I have my margin of error I have my formula for standard error right here. Okay, well, I haven't drawn my sample yet, so I don't know what p hat is or what q hat is. I'm saying how large do I need to sample to make this happen? So since I don't know, I just am going to do the worst case scenario. And the worst case scenario would be 50-50. So they gave me what I want my margin of error to be. They gave me my confidence level. So I did the right z-score, and I said, a worst case scenario, this will be 50-50. Okay, so then you can separate this. This is square root of 0.5 times 0.5 over the square root of n. I just gave everyone their own house. Okay, I never want my variable to be on the bottom. So for this next step, I just multiplied both sides by square root of n so that my variable was never in the denominator. And then I divided by 0.03 to both sides to isolate my variable. So this is what it comes out to be. 1.96 times the square root of PQ. Well, I don't know P and Q, so I just used 1/2 and 1/2 over the margin of error, and that gets me 32.67. But remember, that's the square root, so I have to square both sides, and that gives me 1067.1. So in the very worst case of scenario, if you need to be 95% confidence with a 3% margin of error, you're going to have to sample 1,068 respondents. Okay, so same thing, still confidence interval, still the same formula, you're just solving for a different number. And this time I'm solving for sample size instead of solving for the actual interval itself. So we need to be very comfortable with this formula to be able to use it kind of forward and backward.